So when you are learning Hadoop, we are actually learning distributed systems. Because from a technology perspective, big data is all about volume velocity where the traditional systems are not able to handle it. And you need a larger compute, storage and networks to handle that one. And you get into the system of distributed systems. Now what are the challenges with distributed systems? So when you are getting into distributed systems, you need to have, because there are multiple systems, the nodes are going to fail. So you need to handle node failure. You need to handle synchronization of between the data. So when I say synchronization, I mean, let's say there are two processors. On one processor you are doing some compute. On the other processor you are doing some other compute. Now if this process has to talk to each other, you need to have some amount of data synchronization and data exchange which happens between those machines. So you need a synchronization model when you are handling distributed systems, because some part of the work is done in one machine, some part is done in other machine. So these are the challenges which you need to handle. So you need a distributed synchronization which needs to be done. You need to do coordination across the machines. Not only synchronization of data, you need to handle who will do what and coordination around it. You need to distribute the jobs. You need to break the jobs into small pieces so that each can be done. So that is what this is, distribute and make it smaller. Okay, so because you have a large task to compute. Now there are small machines sitting across the cluster. You want to make it smaller so that each machine can handle that much and distribute a job into all this system. So if you have to build all these systems, that becomes complex. And that is where Hadoop comes into play. So what is Hadoop? Hadoop is going to create a system that will make distributed computing easy. So that's a general introduction to Hadoop. So if we look at from a layman's perspective, so what's going to be Hadoop? The key aspect is you are doing a lot of data processing. There are a lot of things which you need to do because of volume, velocity, variety increasing. You need to get into distributed systems. When you get into distributed systems, you need to do a lot of things yourself to get this working. But if somebody gives you all this in a platter, and that's what is Hadoop. Hadoop makes distributed systems really easy. So that's the technology perspective of big data. That you are looking at volume, velocity, variety, and distributed systems are going to handle it. So now let's look at the business perspective of the data. So I'm looking at business perspective now. From a business perspective or a business team, they don't really care how you process, what you process and so on. For them, there is data and there is huge data. That's what business understands. Now, what business is interested from big data? Business understands that there is a lot of hidden insights into the pile of data. So they want something which will tap into these diverse data sets, which is like variety, volume. So they want to go and grab as much data as possible. Find hidden relationships in the data. Basically hidden relationships or insights, I call it. So they want to find hidden insights in the data and they want to use that insights to monetize or add value to business. So this is what business perspective of big data is. So from a business team's perspective, they don't consider traditional systems and new systems and all sorts. They don't really care about it. All they care is there was data. There is huge data. There is a lot of information which exists. Some which they are able to get some information out. But today there are a lot of other data sets which exist. Like say there is a call logs which the customer is talking to. There is service feedbacks which the customer is filling in. There is social media data. There is a lot of other data within the enterprise where there is a lot of hidden insights and relationships. So can somebody help me find these hidden relationships and help me monetize the data or add more value to business, or I am able to use the business to do more with that data. So that's basically what the business perspective is. So when you are looking at big data, depending upon who you talk to, so if you are talking to a technology audience, this is the perspective. When you are talking to a business audience, this is the perspective. So this is one thing which I want to be clear about. So because business doesn't care whether it's volume, velocity, variety and all, they really care about one thing, which is value. So getting value from the data is their priority. And value from the data is only coming through finding these hidden relationships. Now to find these hidden relationships, you need to tap into large diverse data set, which essentially means you will go back to distributed systems from a technology perspective. So this is how it all starts here. Business wants to get value from the data. So they say, okay, go ahead, look at all the data, make it faster and so on. And then you come back here and say, okay, to handle this, my traditional systems are not going to do it. I need to have a distributed systems to handle it. And hence I need a system which will handle it. And that's the big data systems. So I hope this logically completes your understanding of what is big data and at least a higher level construct on how this is evolving and why this is so popular. Any questions still here? I'll pause so that we can move to what is Hadoop and what is Hadoop getting to you. Any questions?
So this quick question. When we are really thinking in terms of Hadoop or big data, would we really consider any other systems which are surrounded by this data or this big data Hadoop? Meaning like any other systems which are really concerned about it. For example, in today's world, all systems in such a way they are integrated. So would you just go there and then just concentrate on your data and then you just dig through and then you just keep on digging your variety of data and then how you improve it or how you improve performance, how you make value to it. In such a process, would you really mind the systems which are surrounded by all this stuff? Just a blind view. I mean, I just wanted to understand.
Yeah. Okay. So there are two things here, and it's an excellent question to ask at the beginning, so that you clearly get the perspective, the holistic perspective of it. So there are two sets of data which exist within an enterprise. We have what is known as traditional systems, and this is basically our legacy transaction systems, data warehouse systems and so on. So where you have abundance of structured information which is there. Okay, so this is the first thing, and people have been trying to optimize it and so on. So if you look at the journey of this, it started with a single node machines, so single machines here. Then people brought in clusters, okay. Then people moved to appliances, and that is where the trend has been. So people have been trying to optimize the value which we are getting out from this data in different forms. So first it was able to handle through single cluster and appliance, and then we started running analytics on top of these appliances. Okay, so this is how people have been doing traditionally. Now there is a lot of value in this data. Now there is additional set of data which exists in the enterprise. So what we believe is this is only 20% of the data. There is additional 80% of the data in the form of call center logs, website logs, So you have infrastructure logs, basically Linux and other logs. You have contracts and other things. Let's say if you are looking at HR domain, there is resumes and others. You have, if you are looking at emails as another aspects, you have data coming from, for example, if you are looking at a different system altogether. So let's say ERP system, which is there. So some of those would have actually flown here, but there are certain things which are the notes field and other things, the textual attribute, we would have not captured it. So these are all things which exist within the enterprise, which is additional data. Now, this is what we call as dark data. So Gartner terms this as dark data, data which has not been explored before. Okay. And so when you are saying that, okay, what is the other surrounding systems? So surrounding systems are going to be these systems which already exist and they have a lot of value in the data. But this dark data is sitting in some corner or sometimes not captured. So this is what big data is going to do, is trying to bring this data together to a platform and try to get you business value from the data. So when we are talking about additional systems, yes, we will always be dealing with traditional systems. We will also be dealing with new systems to come in. Now there is different approaches. People say that, okay, I am happy with only this analytics, which is analytics on traditional systems. So they keep on optimizing this system, they keep on working on this system and getting you the output. Okay, but they are missing the dark data and what we call as big data analytics. Okay, so that's the perspective which you need to be clear on. Ramesh, hope this gives you
Yeah, that makes sense. Thank you.
Yes. Any other question, folks? So I would always recommend ask any question. It is better because we get into the more details around it. So because you asked the question, I got into dark data and so on. So because otherwise things will not really come. We will follow a structure and go ahead. But the idea is that we should take the maximum benefit. So please ask questions. Don't feel shy about it. And if you cannot speak out, just type the question. I will take it from there. Okay. So that's also fine. Yeah? So don't keep any questions to your mind. Just keep flowing that through. So any questions, let me know. I'm just going to save this and we are going to move on. So it's weekday introduction. I'll send you all this stuff to you guys. So you can see it. Recording will be available. So all that is all set. So now with this context, and since there is no further questions, I will go and understand what is Hadoop. So we said that we are talking about distributed systems. So let's take distributed systems. So we have 1 machine, 2 machine, 3 machine, and let's say 4 machine. Okay. So now each of the machine, what are the characteristics of a machine? Let's say this have 2 CPU, 16 GB RAM. These are all still very small machines compared to the today's world machine. So you have 16 GB RAM and let's say 1 terabyte hard disk. Okay. Network is there, let's say 1 gig Gbps Ethernet cable or some maybe an infinity band also, it's fine. So this is all there in all the machine. So we have, this is node 1 and we have node 2 and so on. So these are node 2. So like this we have so many nodes here. Correct? So there are 3 nodes. Node 3. For now let's assume all of them has the same configuration. So now let's say I want to store a large file of let's say 4 terabyte. It's an hypothetical situation right now. Let's say I want to store 4 terabyte of a file. Okay. Why I keep a 4 terabyte file? No, not really. But yeah, let's assume there is a large file which I want to store. Now there is only 1 terabyte here, 1 terabyte. So there is totally 4 terabytes like this. So what do you want? If you want to store 4 terabytes together, you want to have a virtual system like this. A system which will connect all this 1 TB and expose to me a 4 terabyte machine. Correct? That's what I would expect. I want a distributed file system. I want a distributed file system which will leverage the individual smaller hard disk and give me a feeling, me as a user. So I am a user here. So I am an end user. I have all these machines, but I don't want to individually deal with all the machines. I want to have a system which I can deal with, which will give me a distributed file system feeling where I can see that I have access to 4 TB. Similarly, if I add one more machine here, I will get 5 TB and so on. So what I am getting is, I am getting elastic scalability by adding new nodes. Okay. Then the disk is virtual aggregated and have a distributed file system interface. So this is a distributed file system interface for me. I don't deal with individual hard disk. I deal with a software which gives me a distributed file system view. Okay, so I only interact with this and say put this 4 TB. The 4 TB gets distributed by this system. If there are 10 machines, it has 10 TB and so on. So this feeling is basically what Hadoop will give in the form of Hadoop distributed file system or HDFS. So the principle behind HDFS is to take all these hard disks, get you a virtual feeling and give you a distributed file system feeling. So one part of it is available, that the hard disk is now taken care of. Now what about the CPU and memory? Now when the data is distributed, I want to use the compute also distributedly. So I need a system which will virtualize the compute also. Correct? So I want a distributed computing framework. Which will help me tap into 2 into 4, 8 CPU and 16 into 4, 64 GB of RAM. So I want to have a feeling that I have one single large machine which has 8 CPU and 64 GB. And that feeling will come when I have a distributed computing framework sitting on it. And Hadoop has a framework called MapReduce that framework will give you a illusion that you have a single machine of 8 CPU, 64 GB. So you don't really worry about individual machines. You just give the processing to this MapReduce framework. That guy will distribute the job into all this machine and tap into all these individual CPUs and so on. So you get it. So essentially Hadoop has two parts. It has a distributed file system called HDFS and a distributed computing infrastructure. So what is Hadoop? Hadoop has two parts. It has a distributed file system called HDFS and a distributed computing framework called MapReduce. Okay. So this is the story around it. So what is Hadoop going to bring in? So Hadoop is going to bring you this. Now what is the use of this and why it is and so on. We will come to the details of it and the fundamentals behind Hadoop soon. But when somebody asks you what is Hadoop? Hadoop is two parts. Hadoop has two things. One is it aggregates the disk of any nodes on which Hadoop is installed to give you a virtual aggregated disk feeling, which is called the Hadoop distributed file system. So it gives you a single interface on which you can store and use the data. Similarly, for the compute, which is the CPU and memory, it gives you a distributed computing framework called MapReduce, which helps you visualize or forget the individual machine's compute power and look at as an aggregated compute power on the machine. So any logic which you want to do, you can run it on it. So the way is that you have a 4 terabyte file. The user will push the 4 terabyte file into the distributed file system. Then any logic we want to run on the 4 terabyte, you will write it in a MapReduce framework, give it to this system, and it will execute and come back. Okay, so that is what is Hadoop's introduction. So we are going to go to the next level of it. Why you need Hadoop and so on. Okay, so there is a question like, is it very similar to Teradata architecture? Not really, and there is going to be difference. So once we get into the next level of architecture, we will compare what's the difference between an appliance architecture, which is like a Teradata and it is ours and so on, and what does the difference between Hadoop. Okay, there's a big difference from the way we will. So that is where we will understand what is the bottlenecks, why we cannot use these appliances, what is the issues with the appliances, and what is the fundamental reason why Hadoop was built. Okay, but this is at the conceptual level right now. I wanted to show what is Hadoop. So when you look at Hadoop, you should always think the Hadoop has two parts. There is a distributed file system and there is a distributed compute framework. Okay. Any other questions? So Teradata I have not answered. I will answer it once we finish the architecture of Hadoop and why it is.
So one quick question, Sudesh. Do we really, I know it's open source, but do we really keep an eye on the cost modeling at the moment? Or how people at client location could justify to going towards the big data? Of course, they should have a cost model for it too. So does it really make sense to think at the moment? Or meaning because we are looking at multiple nodes and then multiple systems, right? Obviously, those systems are not probably the monetary systems, but I mean, how the cost model really comes into the picture?
Correct. So we'll come to the cost model. It is going to take a little to deep to get there. So we have to do, so we'll do two things as open items. So we have a Teradata or appliance comparison, okay, which is appliance comparison. So we'll do that, and we will also look at cost, benefits and so on. Okay, ROIs, why people use Hadoop.
Right. At the same time, it is like where this is going to fit in the enterprise architecture. Like we have like application layer and then the infrastructure layer, right? Obviously, it's going to be part of the infrastructure, but how it make difference in an organization.
Yeah, so we'll look at use cases also, how it is deployed. Sure. So that will answer how does it fit into an enterprise architecture and what's the value of it. So we'll cover those things. Okay.
Sure.
So right. Any other question, folks?
Yeah, Steve. One question is, I understand the naming convention for HDFS, and also they are calling for the distributed computing as MapReduce. Is there any logical reason to call that one as that name, or like?
No, MapReduce, there is a specific reason, because MapReduce is a specific programming framework. Okay, it is not a generic distributed computing framework. So when you talk about distributed computing, okay, it's a broad umbrella. Okay, distributed computing frameworks are larger. One of the example of distributed computing is MapReduce, and MapReduce has some limitation, and because of which we go into the next version of Hadoop, which is going to be called Yarn. Yeah, okay. And most of the course is going to be focused on Yarn and the next generation of it along with MapReduce. So our course will purely be focusing on here and going beyond MapReduce. So MapReduce plus other frameworks like Shark is there. No, Spark. You can look at Spark. We have drills, the Impalas and so on. So there are a lot of other frameworks which exist, okay, on distributed computing. So to begin with, we will start with MapReduce. Once we finish MapReduce, we will go to other computing frameworks which are available. So when I say distributed computing framework which Hadoop provides is MapReduce, this is how it all started with. So when we started with Hadoop, the only one computing framework was provided, which was MapReduce. Now people gradually understood that there is MapReduce is not the only distributed computing framework. There are other computing frameworks which can help you in distributed processing. So why don't we use that? And that's where Yarn has come in, and it has brought in a lot of other compute frameworks onto the cluster. Okay. So we'll hold this discussion on what are the other computing frameworks at a later time, because this is where we will do when we start with the advanced sessions. We will look at compute frameworks, distributed computing frameworks in detail. Okay.
Okay.
So I hope the naming is clear now. So it's a one specific one which follows the map and reduce paradigm, and hence it is called MapReduce. Okay. So it has two things called map and reduce functions. So because of that, it is called MapReduce. But it is not a generic term for distributed computing framework. Clear? Okay. So we move on. So now forget everything right now. Let's look at a very simple system, a traditional system. Okay. So I have a web application. So what is a web application looking like? So this is our UI or front end. So behind the front end, you will have an app server. An app server which is going to give you the logic, business logic. Correct? So this is where the business logic will be written. Then you will have a database, the data tier. So you will have what is known as the database tier. Okay. So in this case, it's the database is data processing is done here. Now usually we get confused that data is stored here. Data is not usually stored here. Data is stored in another machines, which is the storage layer, the SAN and NAS, NFS. So the storage layer will be like, it is a storage area network, network attached storage, or it could be NFS mounted storage. So depending upon how it is. So you basically the database connects to this storage, process it, renders the data here, it comes to the UI. So by the time the UI comes, it is usually very less data. So it's very few rows. Because if you have more records anyway, UI will not be able to handle. Here there will be large number of rows. And here it will be very large number of rows. Almost everything will be moved to very large. So there are 2-3 problems. One problem which we are seeing is the data has to physically move to the processing. So one of the problem is data moves to the compute. Now if you are looking at terabyte, 1 terabyte, 2 terabyte, this is not a big deal. But if you are talking about hundreds of terabytes, 100 TB plus, then this movement is going to cost a lot of bandwidth and it will be slower. So this is one bottleneck which you will usually get into, which is the network bottleneck. I hope you guys agree. So when you are looking at performance tuning, usually this will become as a bottleneck where data has to move across the network. The second biggest bottleneck usually is the IO bottleneck. Why is the IO bottleneck happening? Because IO bottleneck usually happens because you have a disk. Disk has a spindle on which the spindle rotates on the disk, or if it is a SSDs, you actually have an access models around that. So what really happens is in an IO bottleneck, there is an access bottleneck for the data, because you try to go after the data again and again, and then there is a throughput issue which comes in. Because let's say you want to take 100 terabytes out of the disk, there is limitations around how much throughput the disk can handle. So this is your second problem. Now the third problem is, for every record you have to search, or you have to seek the record and then fetch the record. So let's say you are looking at an RDBMS situation. So let me take the example of a hard disk. So this is a crude way of representing an hard disk, let's say. So this is how the hard disk looks like. Let's say the data is sitting here. So first time when a record is to be fetched from the database, the spindle will rotate and it will go to a particular position. Okay. And once it reaches the start of the record, it will start fetching the record from there. So records are usually of how much size? Let's say a record will be like 4 KB or let's say 10 KB. So once it fetches that record, it will get that record out. Then it fetches the next record, fetch the next record, and then get the again 10 KB and so on. So if you look at any IO operation in a database kind of a world, you fetch the record, then get the data. Fetch the record, get the data. So you have a pointer to where the records are, which is kept in an index, and you take that index, go to the record and fetch the data. Now the problem is, if you go further deeper into it, this seeking the record takes time, and then fetching the record obviously takes more time. But this seek time can be totally avoided. If seek time can be totally avoided per record, if we can store bulk of the records together. So let's say I store 100,000 records together. Okay. So I store, let's say, 1000 records together. 1000 records are stored continuously. So what happens? If I have to do, I will fetch the record and get 1000 records at one shot, which means I have reduced the seek time. I have reduced the seek time 1000 times. So let's say if a seek time is usually in a millisecond phase, let's say there is a 1 millisecond seek time for a record. So with 1000 record itself, I have saved 1 second. So look at 1 million and 10 million and so on. So I will be saving lot of data, time, if I can store records which are in a continuous order. Now why don't we do this in an RDBMS? In an RDBMS, the queries are very pointed. They want to go after a single record at it most of the time. They want to update a record, they want to insert a record, they want to delete a record and so on. So in big data workloads, there is not that kind of a requirement. When we are processing a petabyte of data, we don't care about individual records. We want all the records to be aggregated. We want all records to be filtered. You want to do processing across the record. So the number of records which we usually use in big data is huge. Using that construct, storing the data in larger chunks is much more valuable. So So big data always follow the principle of block storage. What is block storage? Storing continuous large chunks of data continuously. Store large chunks of data continuously to avoid seek time per record. Is this clear? This is a very important concept. Why you need a block storage? You need a block storage because to avoid the seek time for every record. Now, the other thing which we also talked about is we have access bottlenecks on the data. So we need more throughput. What is the way to solve this problem? You give more disk. If one disk is giving you 100 bits per second, so let's say 100 GB per second is what one disk is giving you throughput, or 1 GB per second. So if I have 10 disks running in parallel, so I will get 10 GB per second. So I can improve the things if I adding more disk, more throughput, and this is known. Now this is how the SAR and others works. They keep on adding more disk and give you more spindle so that more seek will happen together and more output will come. Now in big data what we are saying is we want to avoid this network traffic. So we cannot have lot of disk kind of a concept. We want distributed disk. So we are going to have distributed disk, but each disk will give you more throughput, because the more number of disk which you have, the more number of throughput you get. And how do you do this? You add more and more machines. So here this is done through adding more machines. So you add more machines, which we talked about the elasticity. So with adding more and more machines, you are actually improving the throughput. By storing it in blocks, you are actually avoiding the seek time. By moving the compute towards the data, you are avoiding the network bottleneck. So how is this done? This is done using the MapReduce framework. So MapReduce framework gives an ability to move the compute towards the data, and we will see how that does in some time. Okay, so these are the three essential characteristics of big data. That is, move the data towards the compute. No, you avoid moving the data towards the compute. That's one thing, sorry. The second thing is you should have more and more disk in a distributed fashion to increase your throughput. You should store the data in blocks so that you can avoid seek time. So all of this is done by Hadoop. So from a big data optimization perspective, Hadoop actually does all of those. So Hadoop does data local processing, which is the first problem. It supports elastic scalability to increase throughput. Okay. Now, does block storage to avoid seek time. Is this clear? Now there are more things Hadoop does, not just this, but I hope the concept of these three things are clear. Any questions on what Hadoop does and why it is doing that from a fundamental perspective? This is where you will see a difference. Yeah, go ahead, sorry. Go ahead.
So it will do the what we call like data fragmentation kind of techniques.
Correct.
So that like it will store all the related data in sequential sectors.
It is not all the equal related data. What it does is it takes a file, chunks it into blocks and stores it block by block. Because in Hadoop, in a big data processing, we will usually process most of the data. Okay. So there is nothing like related data. Let's say you are processing a file, you have to process the whole file. So you are going to process it continuously. So if you split that file into blocks, you can read the blocks individually, correct? So that's what the idea is. It is not like it is fragmenting the data using the affinity of the data towards each other. There is no affinity concept here. Okay?
Okay.
Any other questions? So remember these 3-4 things which is very important. One is don't move the data across the clusters. Don't move machine data across the nodes. Avoid movement of the data. For that you need to have a data local processing framework. When you need to use the local disk as much as possible. Okay. So once you have local disk as much as possible, if you add more number of machines, you get increased throughput by having more number of disks. If you store the data in blocks, you can avoid the seek time. And that's what the 3 things which Hadoop will do. Okay. So now we will proceed further and say what else are the things required. What else?
So I have a question regarding the seek time.
Yeah.
Is the seek time, does this scenario apply only for unstructured data, or does it apply for structured data where, say for example in Oracle you're seeking 1,000 rows at a time? And wouldn't there be a seek time for a block too in that case? How do you compare seeking 1,000 rows in Oracle as compared to, say, a continuous block? There should be a process of seeking a particular block too, isn't it? How do you compare both those scenarios? And how do you say big data is better in that scenario?
Okay, block access. Okay, so this is the concept of block access comparing with traditional system. Okay, so that is what we will do. So let's take an Oracle example. So I have a data set. So this is an employee file, let's say. It's the easiest to understand, so I take the employee file. It has employee ID, age, gender, salary, address as the fields. Okay, so these are the fields in it, and this is a huge file because there is a lot of employees in it. We are looking at, let's say, 1 TB of 1 million records for now. It's still smaller. Okay, it could go to 100 billion also. So we will say that there is 1 million record. Now if you have to store this 1 million record in Oracle, what Oracle would do is take the disk. So this is, let's say, the disk. As the record comes in, okay, it will keep writing into the disk. Correct? So as record comes, so 1 record would have come, it has written. Then the 10th record would have come, then it would have written, and so on. So the record writing is not going to be sequential or anything. It will be fragmented. And the reason it is required that way is because it stores the index of the data in some other location. So you have an index sitting somewhere. So this is an index where it will have the pointer to each record where the index, where the record is going to point. So you have an index and you have a record pointer to that, and the data is here. So data is fragmented, which is okay to him. Now, when you have an insert, update and all, it becomes very easy because it goes to the index, finds a particular record, seeks that record, updates the record and comes out. Similarly, update, delete. So as long as it's record level operation, it is very efficient. Okay. Now let's say you are doing a scan of the entire table. So what happens? If you are doing a entire table scan, it is slower, and that's known to everybody because it is going to seek record by record, and fetch the data. So it is going to do a seek record and then fetch record for all the 100,000, 1 million records. So this is what is happening inside the database. Every time a seek is happening, every time a fetch is happening. Now let me run a query onto this. I am trying to run a query. My query is select sum of salary, group by gender, where age greater than 25, group by gender. Okay. So this is the query which I want to run. Now if you look at this query, it has to pretty much fetch the entire table. Okay. Now it is going to do seek record, fetch record for all the record. As if it seeks it, it will eliminate age greater than 25 and it will aggregate sum of 20 salary and give it to you. Correct? So this is how the traditional system is going to work out. Now let's look at how Hadoop is going to do this. So you will get this. So let's say Hadoop will have multiple machines. Okay. So what it will do, it will take this large file and push it into it. So let's say for now, this is the file. Yes, so this is a small file, the 1 million record file. So when Hadoop will do it, it will break this file like this. It will break it here, here, and here. Let's say it breaks it into some chunks. So what it will do is, it will take this first part of the file and store it here. Okay. It will take the second part of the file and maybe store it here. Takes the third part of the file and store it. Takes the third part of the file, store it here. And it may be the fourth part, it will store it again here only. Let's say for some reason. Okay, so this is the files which are getting stored now. The files are stored. Now if you write a query, so you can do the same query in Hadoop as well. Okay. So Hadoop, it will be converted to something called as MapReduce. So let's say for now assume that there is a MapReduce kind of a code which is there. Okay. Now what Hadoop will do is send this MapReduce code here. It will not pull the data. Okay. It will push this MapReduce code here. Okay, so let's assume this is the code. Let me fill it. So this is the MapReduce code which we are looking at. Okay. So similarly, the MapReduce code will come here. And similarly, the MapReduce code will come here. So the code is moving towards the data. Okay. And this code is going to operate only on the data which is locally here. So that is how the data local processing will happen. Okay, so data local processing will happen. When it fetches, what it will do, it will fetch the entire block. It will not fetch record by record. It will take this whole thing together in this program. Similarly, this will take the whole thing in this program. You will see. So there is no record by record seeking which is going to happen here. At the same time, it is not moving the data out of this machine to a DB engine. It is doing it locally there. So this is how the difference between traditional system and the Hadoop system is going to be there. In Hadoop, it is going to read this whole block together. While in traditional system, it is going to read seek by record by record, record by record. So the seek time is still going to happen. It is not data local processing because there is a DBMS engine. So let's say this is a disk and this is a DB engine. The data has to move from the disk to the DB engine. So record by record, it will move to the DB engine to do the processing from the disk. Okay, here. While in this case, the disk is local here, the processing is local here. It is just going to read the whole block at a time and just process it together. The fundamental assumption is that Hadoop is not going to support a record level operation. Record level operations are not supported. Only bulk operations are supported. Okay, so all read and write will be all in bulk. It will never do a record. So you cannot do an update record in Hadoop. You cannot do an update record in Hadoop. You cannot insert a single record in Hadoop. you have to insert always bulk record. You cannot delete a single record in Hadoop because there is no record level operation at all. All are the bulk record, bulk operation. So this is Hadoop's limitation. Is that clear? Aruna, does it make sense? Hello? Okay, thanks. So that's makes it clear to you guys. So what's the difference between Hadoop and traditional systems? How does the whole operation works?
So quick thing, Sudesh. So now it indicates the obvious thing is that Hadoop is not meant for any traditional website applications. Let's say you want to see some front-end DML operations performing in the web page, and then you wanna say bring up or insert the data to your database or the traditional MVC layer type of kind of a thing. So this is just to bring bulk data, move between the your analytical reporting system to your storage devices. Is it still is like kind of a workable solution between your MVC?
Okay, so there is something called as noise. Yeah, it is. So there are two kinds of technologies. When we look at the technology landscape soon, okay. So technology landscape, we will see it. So what I covered is just the Hadoop batch. So Hadoop is a batch processing engine. Okay.
Okay.
So when you look at Hadoop, Hadoop is only a batch processing engine. So which essentially means it can do only batch work. But on top of Hadoop, you can have a NoSQL database like HBase. Okay.
Oh, okay.
Which you can do real-time access. Real-time, you can insert, update everything. So what it does is it will do all the operation in memory, and at bulk it will commit. Okay. So HBase, when we look at it in some days, you will see that HBase can do lot of processing like that. Okay, where you can use. So Hadoop ecosystem can actually support lot of interactive services also. So don't get constrained right now there.
Okay. Yeah.
Okay. So those are add-on layer on top of the Hadoop. We need to look at the Hadoop ecosystem components itself. Okay. So right now we see that you can run MapReduce, but you don't need a MapReduce. Same query you can use a technology called Hive. So Hive is a SQL over Hadoop. So you write this same query in Hive, then Hive will automatically convert that to MapReduce. You don't need to write a MapReduce. Hive will automatically convert to MapReduce. Okay. So similarly, there are a lot of technology landscape which exists. So when we look at the technology around it, we will come to that. So what I'm trying to do is I'm trying to bootstrap gradually up there. So if I explain everything together, it will not help. So first we'll go to grassroots, understand the fundamentals. One by one we will go up the layer.
Got it. Thank you.
Nice. Any other question, folks? It's better to ask the question again. Thanks to Aruna for asking this. Otherwise, this would not have been so easy and transparent to you guys.
That makes really sense. Thanks to Aruna for sure.
It gives a lot of details into it. So this is comparing with traditional systems. So folks, keeps the questions coming. It will help you. What is this? This is okay. So now we understood the few things about Hadoop. Okay, so let me go back to my mind map, which will give me my consolidated view of what all I need to cover. Okay, so there are slides and so on around this, but the problem with slides is they just tend to be too vague at some time. So that's the reason I don't prefer slides at all. I prefer to keep the session interactive. So from a fundamental perspective, we covered data local processing. This is what we covered. We looked at avoiding network traffic. We said block storage to avoid seek time. We said we need more disk to increase throughput. Okay. So there are two things which we have not covered. Hadoop as a concept of worm. which we gradually came in here. Which means what we are saying is Hadoop as a system is meant for write once and read many times. So usually looking at a analytical workload, okay, if you are looking at an analytical workload, it is usually like this. You get the data from various source systems, you dump the data somewhere and then do a lot of different types of processing on the data. So it is usually write once, read many times. You never do an append on a record even in a data warehouse. Usually you try to avoid append, updates and so on. So Hadoop is a system which is usually trying to do a write once, read many times. Hadoop will support append on a file. Okay, the append feature is there. Append is like adding more blocks. So I will show you how it will. So let's say this was the file, and all of a sudden you said, no, I have another 100,000 employee coming in. So I added one more set of things here, chunk. So I can do that, and then I can store that chunk in some other location. So Hadoop supports appending a file, okay, but it doesn't support updating a record in a file. Okay, so that is where we say it is write once. You can write the once and read it many times. This is the kind of workload we are getting into it. So Hadoop is write once, read many times kind of workload, and it's an append only feature. Any questions on this? So these are all the fundamentals of big data, not only Hadoop, any big data systems which you take in, okay? Because whatever we covered here, the fundamentals behind the RDBMS and so on, this is fundamental to any large scale data processing. So the thing is, we don't have to worry about these fundamentals across. It is applicable across the big data systems. So it's not Hadoop fundamentals alone, it's all the big data fundamentals. So Ajit had a question. So how do we do update? That's an interesting question. So it only supports append. How do you support updates? So in a Hadoop ecosystem, updates are supported only in two places. Okay. One is a NoSQL technology like HBase. We will cover that separately, how a NoSQL gets updates. If you want to do updates in a file, you actually create a new version, new record, and say this is the latest. And in your processing, you only take the latest. So let's say you want to do an update on this employee file. You will attach another set of updated record on the employee file and give a new version ID to it. So ideally, if you want to support upload on an employee file, you should have a column called version. And when the first thing comes, you just put the first version. You add another record, you put version 2. And whenever you read in such a way that you take all the latest version upfront and give the record back. So this is what you do as part of update. So that's a technique which you need to implement. Hadoop doesn't give you update by default. If you need an update, you need to write the business logic in such a way that you handle updates yourself. Ajit, I hope.
How far we could add those blocks like that? I mean, if you as many updates, as many blocks, how far you go like that?
No, we usually make it as a bulk blocks. So you don't like every record you change, you will give one more block. That is like it's going back to record level thing. It will violate the fundamental principle of block level storage, correct? So what we do is we batch all the updates together, okay, and then create a new block on top of it. So let's say if you are doing a daily processing, so every day you get updates. So every day there will be additional blocks added at the end of the file. Okay. So Hadoop is not used for transactional system at all. Okay.
Okay.
So Hadoop is not a replacement to any transactional system. Okay. Hadoop is only for analytical system. So where you have large volume of data and you want to do lot of processing. So it is going to be more at a data warehouse replacement at one point of time. It is not an all TP replacement at all. So if you look at the architecture itself, this will be the source systems which you will have, different source systems. Okay, some will be like your existing traditional RDBMS. Okay, RDBMS. You will have log files coming in from different systems. Okay, you have some external data like social and others coming in. So what happens is traditional RDBMS are our transactional systems. So these are your transactional systems, which will include the ERPs and other things, transactions. So the Hadoop should be looked at as an extension. So let's say you already have a warehouse today. Okay, so let's say you have a data warehouse here. So what people do is we try to augment that warehouse with the Hadoop platform. So let's say the rest is a Hadoop platform. So this is your Hadoop platform. Okay. So there are 2 or 3 architectural patterns here. One pattern is saying that replace the data warehouse and put everything into Hadoop. Okay. Other is let this RDBMS continue to feed the additional warehouse. Let the logs and others, because we are unstructured, let it come to Hadoop directly. Let all the other unstructured data directly come to Hadoop. So this will be like the unstructured content which is coming. So you will do a lot of processing in Hadoop itself. Okay, so here you will do MapReduce processing on Hadoop. Okay. You will create structured outputs from this processing. So after the processing, it will be mostly structured. Okay. Now you have 2 choices. One choice is you will move this structured back to this warehouse and let your existing reporting system use this additional augmented data. Okay. So this is option 1. Option 1, architectural pattern. Okay. Where you do unstructured processing outside and push it back to your existing warehouse. Okay. The other processing is that this will anyway go here. When we are doing this RDBMS, we are doing lot of processing here. Correct? We are doing data warehouse processing. This is usually done through the ETL, Informatica, data stage and so on. Then there is some processing which you do here in the database. You do some processing here by transforming the data and creating aggregated data and so on. Correct? You do this. Now, so this is your final output. So semantic layer of the data. So what happens is there is architectural patterns where people try to avoid this whole thing. Why should we spend our money on doing all this processing on a ETL server and pay the license cost for it? You could actually take this data, dump it to Hadoop. Okay. So this is structured content now. Then what you do, you again do all this ETL processing inside the MapReduce framework. Okay. Create structured data, push it back and go out. So you have eliminated this. So this is another constructs which people do. Eliminate ETL processing. You also move this processing to here. So that data warehouse is only used for mostly storing the whole thing and lightweight processing and rendering the data. Okay, so these are the 3 architectural patterns which we have for an augmentation of the data warehouse. It's called as augmented data warehouse architectures. Okay, so this is all technology solution. These are not only the big data use cases. This is all technology architectures. Okay. Any questions on it? I hope this gives you a big picture that Hadoop is not used for transactional systems. It is only used as a analytical platform. You can use it for mainly unstructured content. You can use it for structured content by removing the CPU cycles which you use it in the ETL processing or in the data warehouse systems. Is that clear?
Yes.
Go ahead, ask the questions. Yeah, we can process structured data in Hadoop, Dheeraj. Yes. That's the reason I brought the structured data there. Okay. Now, Achyut, I have a question. How is the block size determined? We will come to that block size determination again when we look at Hadoop in detail more. Okay. So we need to look at HDFS in more detail. Then we will cover the block size, how it is decided. Ideally, it is, if you look at it from a one-liner answer, it is based on the average file size in the cluster. And why it is decided, this answer will come when you do HDFS in more detail. So I'm not going to do right now there. We will take a little bit more time to cover that. Sorry, Achyut. Okay.
So, could we comfortably eliminate the data warehouse part as well, or is just still we need that to present it to the reporting layer?
See, what happens is, today, if you look at the reporting layer, that's a bigger constraint today. The reporting layer is dominated today by players like Tableau, ClickView, Cognos, MicroStrategy and so on. So the problem with these guys are, there is a lot of investment already gone into it. Okay.
Yeah.
And there is no point replacing this thing because there is no different evolution of technology which has come to. Okay. So these technologies are still matured enough to handle any kind of data, except they are still having some limitation with unstructured data. But most of the time unstructured data is converted to structure. So this reporting layer still happens to be dominating. Now these guys give connectivity mostly to databases. So that is the reason this is not eliminated yet. But I don't see that in near future they might all say that, okay, I'll support anything else. And let's say report out of HBase directly and so on. Okay.
Yeah.
So in that case, there will be this elimination. But right now, again, since you have already invested in your warehouses, you already have the appliance with you. Okay.
Yeah.
There is no point to say that just junk that into some corner and I'm going to bring a new infrastructure. That has never sold it, because many people will lose their job because of that. Why did you invest in technology? So we usually don't recommend it. We don't recommend to go there.
Small scale organizations are organizations which are about to start having some kind of warehouses. They could directly go to Hadoop and then.
Yeah. Then what? Yeah. But we still use, in that case, we use MySQL and Postgres. Okay.
Okay.
Which are open source, and because we can still rely on these reporting tools to get a quick benefit. Okay. So you eliminate the appliances, but you use something lightweight like this. Oh, the last option is you actually build visualization using JavaScript. So D3 library is there, which is very powerful for visualization. So you build that and you create a data service layer below it. Okay. So there is a data service layer which is created on top of HBase or any other NoSQL systems, and we render. So the new architecture is usually like this: HBase or NoSQL. Okay. On top of Hadoop, and then D3 visualization coming. So if you are looking at a new architectural stack, it will be bringing data to Hadoop platform, a data service layer sitting on top of it, and a NoSQL structure obviously for the structured data storage, large scale structured storage with high scalability, and then a visualization engine sitting on top. So this is how it all works together. Okay. So this gives you an architectural foundation to big data. Clear? So only question which I have not answered is how is the block size determined. That we will do it for when we do the HDFS operation. Okay. Any other questions, anybody? Okay, so we move on to the next layer. So we looked at, now there is one principle called schema on read and schema on write. So let's finish this as the fundamentals. and then we can go to Hadoop. So let me cover that. Where did it go? Right. So we are trying to understand what is schema on read and schema on write. This is again a very important concept. The entire Hadoop reside on this. So what happens? You have a data. Let's say look at traditional system first. Okay, so let's look at how traditionally we will handle data. In a traditional system, what you do is you take the data from, let's say, your transactional RDBMS. Then you bring it to, let's say, your analytical system, which usually is again an RDBMS kind of a store. So if you want to bring this data to this your data warehouse layer, first you need to decide the schema of this information. So before bringing any data, we need to decide the schema. Okay? We do a data modeling. So we do a data modeling of the warehouse and we decide the schema. We decide the attributes. We decide the data types. We decide the relationships between the data. We decide the constraints on the data. It can have nulls, not nulls, and so on. So these are all things which we decide when you bring the data. Then we load the data. When we load the data, what it will do? It will check for the schema. Basically, it will validate the schema. And once it validates the schema, it will load the data to RDBMS. Clear? So this is what we essentially do in a typical RDBMS system. Clear? So what essentially this means is you need to be upfront aware of the schema and the constraint before loading the data, and so that schema is on write. When you are writing the data, we are applying the schema. We are enforcing the schema during write of the data. Hadoop doesn't work like that. Hadoop is like a file system. In a file system, you don't have any schema. Correct? So Hadoop is like a file system. So what you do is you have your RDBMS data. You just bring that data straight away and dump it. You don't worry about the schema at all. Just dump it. It will be file 1. Let's say this is employee file. Okay. So this is going to be employee file 1. We have some social data, let's say. We bring that in straight away without even thinking what it is and so on. Just bring the data. So it will act like a dumping yard. Hadoop will act like a dumping yard. So this will be social data. Now when you want to analyze, see, if you bring all the data, what you want to bring it, because we want some user to run some analysis on the data. So user is going to run some analysis. When he runs the analysis, he is going to define the schema. He is going to say from the employee file, pick up employee ID, age, and let's say gender. And the format of the file is like this. So he will give the format of the file and say this is the schema which I need to pick up. Similarly, we will say, okay, go to the social and pick up, let's say, the messages, tweet messages or handle or something, and this is the schema for that. Okay, so you will say that pick me the user ID, location, and tweet from this social data. So you will apply the schema on the fly when he is reading the data. Then it will fetch the data, parse the data, fetch it, and then do the processing on the fly. Why it is done this way? It is on-demand schema. On-demand schema. See, this is what is called a schema on read. So when you want to read the data, you apply the schema. It gives you two benefits. One is there are a lot of unstructured content which is there. Now one thing is, if you just don't bring the data in, you are losing it. Now if you try to structure the data, you don't know what all analysis you want to do in future. You want, let's say 5 fields today. Tomorrow you will need 20 fields. So if you don't bring that field here upfront, you will be in trouble later on. The storage on Hadoop is cheaper. So what we do, we bring everything into Hadoop. Then we say, okay, now I have everything. My analysis only needs 4 fields. Let me put a schema for 4 fields, bring the data, analyze it, get out. And if I want to do that repetitively, then what I will do? Okay, I'll run one batch process which will populate my updated schema in a different file. And I will always use that updated file rather than going to the base file. So this is how the Hadoop ecosystem works. The Hadoop ecosystem works on the schema on read principle. Because the idea is that there is a lot of junk data which will exist. We cannot do the structuring upfront, and if we try to do structuring, our projects will never finish. We will not get agility. We want to make it faster, and hence it is better to just dump the data, and whenever somebody wants to do analysis, give the schema. Anyway, it's a large scale distributed computing. It will anyway parse the file on the fly and get you what you need. So this is the concept of schema on read. Is that clear? So this is schema on read. Any questions? So for example, tomorrow you say that I have got some finance data. So I will say forget anything, just dump it to Hadoop. I don't know whether I want finance data or not, but you just dump it. Tomorrow we'll see. Then tomorrow some analyst comes and say, oh, I want to merge the finance data with the employee data and see how the performance looks like. Oh yeah, so you will say, okay, what is the schema of that finance data? Okay, this is the schema. This is the fields which you need. Now put a schema to it, read the data. Okay, employee file, we know this is the schema. Put these 4 files, bring the data out, merge the data on the fly, do the analysis, give the result. Done. So that makes Hadoop so flexible. Any questions? No questions? Then I think we are done with the fundamentals of most of the Hadoop from an architectural and conceptual perspective. We can move how Hadoop works. Okay. So fundamentally we have covered here all the fundamentals of big data. Okay. So now what is big data we will cover sometimes later. We look at what is Hadoop, how Hadoop works, and how is the distributed file system working. So let's go look at that. Okay, so this is, once we finish we will be able to do all that. So let's look at the fundamental behind the HDFS design and key characteristics. Okay, so let's start with that. Okay, so we are looking at HDFS design in detail. So let's say we want to build a distributed file system. So you have 4 machines, or let's say we take 3 machines this time. Now as an end user, I want to have this virtual feeling. I want to connect to some system let's say this is the user. I am connecting to a virtual system called a Hadoop system. So this is the entry point. Okay, so this is Hadoop interface, and I want to see that I get my, let's say each one is 1 TB. So I want to see a 3 TB system. How does this happen? For that, Hadoop has a machine called the name node. So there are two processes which runs. So this is the master machine, and this machine runs a process called name node. So these are all Java process. Okay. And all the slave machines. So these are all slave machines. So these all will run a process called data node. So this is also a Java process which will run. Okay, so let's understand what each of the roles and responsibilities of each of this process and how they give you the virtual feeling. So this is the data node. Remember, this is data node is a Java process. I'm going to make it here Java. This name node is also a Java process. So it runs under a JVM umbrella. Okay. Now what is so let's say you have a file. We said we have a huge file. This is the employee file which I want to move it to Hadoop. So this is employee file, and I want to push this employee file into the Hadoop ecosystem. Correct? So that's what my goal is. So let's say this is a 1 TB file. Okay. So what the name node does is it actually stores the metadata about the file. So it says where this file, what is the name of the file, what are the pieces of this file or blocks for the file, and where it is stored. So this is the information which the name node will have. So name node will have the name of the file, the location of the file, where it is stored, and so on. So this gives you the metadata about the file, and the data node actually is responsible for storing the physical blocks. So it will say block 1, block 2, and so on. So when the file is broken down, these blocks are stored into the data node here. Okay. So these are like the blocks which are physically stored on this machine. These blocks are just like another files on the file system. The only thing is only Hadoop knows how to merge the files together. So these are all blocks, raw file system blocks. So when you want to store 1 TB of the file, the files will be broken. Okay. Now who is breaking, how is it breaking, all that will come. But these files will be broken into blocks, and each block is going to get stored by the data node in these forms. And this name node will have the metadata which will say that this file consists of 4 blocks. This is block 1, block 2, block 3, block 4. So it will say file 1 has 4 blocks. So let's say this is called employee file. Employee file has block 1, block 2, block 3, and so on, or block 4. Okay, so this is where it will say, and it will say block 1 is stored in slave 1, slave 3, and so on, because the same block will be stored multiple places just to have the replication. We will come to that replication later on. For now, let's say blocks, we'll remove the duplication for now. Just assume that block 1 is saved in slave 1, block 2 is saved in slave 2, block 3 is stored in slave 4, and block 4 is stored in slave 3. So randomly it will store. Okay. So this information is there here. So now when you put the data in, the name node will give this location, and when somebody wants to get the data back, he will just assemble the file back and get it. So the whole idea is that any file which is there, you break it into it, store small chunks of it. Where it is broken and stored is kept it in the name node. So you can always get the file back by just asking the name node. Okay, so this is the first view. So we are going to go at least 5 level deeper view of this. So this is level 0 view of HDFS. So in this level 0 view, all it is I am telling is, you have a file system interface to save and get the file. So you put the file, get the file. You get an interface. Okay. The name node is going to store the metadata. Data node is storing the blocks. This is level 0 view of HDFS. We will go to one level deeper. Like this, there are 5 levels deeper we need to go to understand HDFS in detail. So, any questions on the high level view of HDFS? Okay, so no questions here. I am going to go to level 2 view of HDFS. So now when we go to level 1 view, so let me use the same picture. I'm just going to go to level 1 view. So now you have a file. The way this whole thing works is there is something called as Hadoop client. So this interface is actually provided by what is known as Hadoop client. This is a jar, just like the JDBC jar, which you embed inside your user program. So this part is kept inside the user program. Okay. So this is embedded like JDBC jar into your program. All it has is, it has a configuration file which specifies where the name node is. So the configuration specifies where the name node is. So once it has that configuration, this client will connect to name node and say that name node, I have this one file which I want to store. Can you store the file? Immediately name node will make an entry in the memory of the name node, which is the metadata. So name node's metadata is stored in memory. So this is something which you need to remember. Name node's metadata is in memory. So it will make an entry in the memory that there is a file 1 which it is to be stored in, and the storage location is specified using a unified resource identifier. So URI. So URI defines the file location. So it is just like this /user user1 employee file 1. So this is a URI for where the file is going to store. So it just follows our directory convention. So the URI for the file is like this. So you can say that, yeah, there is a user directory, there is a user1 directory. Under that there is employee1.txt file which is stored. But from a Hadoop perspective, this whole thing is a URI. So it only stores the URI. There is no concept of directory as such. It only stores the URI. Every file is stored as a URI. So this is the URI. And the first time when the user asks it, it will just give the URI and a handle to this URI back. So a handle to this URI is given to the client back. So that whenever he wants to push the block, he can tell that, yeah, this is the URI, I want to push the block. So what happens is, the block size is decided upfront. So block size is a configuration. Block size is a configuration decided upfront. Now for now, let's assume the default block size is 64 MB. So it will chunk this file into 64 MB. So this is a configuration which is available to this Hadoop client. So what it will do, it will start reading this file, and when it reaches the 64 MB mark, it will cut it and tell name node, I have a block which I want to store. So the name node will say, okay, block 1, store it in slave 1. So then what happens? The Hadoop client will ship the data to slave 1. It will connect to data node of slave 1 and say, I have this block, please store it. The data node will then receive the file and store it here. So this becomes block 1. Okay. So like that, the second block will be read. It will, let's say it decides to ship it here. So the block 2 will be stored here, and so on. So this is how the blocks are stored. So this is your level 2 views of HDFS. So now in this, what you understood was two things. Each file is stored as a URI. Okay. Each file is stored as a URI. The second thing is there is a name node process which is storing the metadata in memory. There is a Hadoop client which is responsible for doing all the program management. It will have a configuration file. The blocks are streamed to the data node using the Hadoop client. The name node only will instruct the Hadoop client where to store it, and thus Hadoop client will actually contact the data node and store the blocks individually. So this is how the file reaches the data node. Any questions on how the...
Sudesh, I have a question regarding the URL.
Yeah.
You mentioned that the client contacts the name node when it has a block which has, say for example, the basic block size of 64 MB.
Yes.
Does the client contact the name node even before it starts chunking the file?
Yeah, the first time it will contact because it needs to get the handle of the file. Okay. So when you open the file handle, it will first make a call to name node and get the handle of the file. That time
I would like to stop you out there. When you say it needs to get a handle of the file, I'm talking about saving the file. In that case, the name node doesn't know the existence of the file. So is the file present on the client side initially, or at some other place we're talking about?
No, the file is at the client right now. Name node has no awareness of the file. Name node is a system. So the file is with the user. The user wants to interact and store this file into Hadoop. So first thing what it will do is, it will say, I have this file which I want to store it to you. It will not tell the block size, anything. It will just say, I have a file which I want to store it. Okay. And this is the URI of the file. Because there is initial checks which name node needs to do to confirm that whether it can even store that file.
Okay, alright.
Okay, so once that confirmation comes in, the handle is come back to it, it will now start reading the file and then ask name node, I want to store this. Okay, then it will give you the block, and then the block gets streamed to data node and it will store the block.
Is the Hadoop client a part of the user system, or does it exist separately?
Hadoop client is a jar which is provided by Hadoop, which needs to be embedded into your program if you are running a Java program. Okay? Or you can install in any machine called, let's say you have a Linux machine, you can install Hadoop client there. You need this to connect to Hadoop system. So any interaction with Hadoop is done through a Hadoop client. Just like the JDBC. If you want to interact with a database, you need a JDBC driver. Correct?
Right.
That is the same principle here. If you want to interact with Hadoop, you need a client.
Alright, thank you.
Thanks. Yeah, you can go on mute. Yeah, any other questions, folks? So this is the interaction. So first the file handle is got in, because it needs to confirm whether the user who is storing the file in that URI has the proper privileges, whether there is enough space left in the Hadoop system to even accept a block of data and so on. So to ensure that, there is a first call made where the handle is get, then the second request is for getting the block, the first block, then the third block and so on. So this is how the interaction happens with the name node system. Okay. Now let's go on and see the next part of it. So now we know that there is a Hadoop client which is responsible for doing all the jugglery. The important thing to note is the file never goes to name node. The traffic on this name node is only lightweight. The file moves from here to the user machine directly down to the slave machine. The master machine is not aware of the content of the file. The content never moves to name node. Only the metadata moves to name node. So every time a block is there, it will keep on asking. So when it stores the next block, it will ask. So at the end of it, when the file system reaches the end of file, it will say to the name node, I am done. The file is saved. At that time, the name node will commit the memory to be available to everybody else. Till that time, if somebody asks for this particular file, he will not be able to get the file. Till the end of file is reached and the Hadoop client has committed to the name node saying, I am done storing the file. Once the file is stored properly, then any request from any other Hadoop client will give the file out. Till that time, it is not given. Okay, so that is something called as commit at the end of it. End of the file, it is committed and the name node's memory is now available to everybody else. So that's a very important thing which you need to remember. And that's about level 2 of the file. Okay, any other question? Any questions on this? So this is how the level 2 which we have seen it, that in this case the commission is happening and the files are stored. Now the biggest problem is that the files are chunked and stored it. So if there is a problem, if this machine goes down or this hard disk crashes, the entire file is not readable. For that, Hadoop stores the file in multiple locations. So it replicates it. So that is called the replication factor. So you can set the replication factor. There is a default replication factor. Okay, so default replication factor is 3. And there is a replication factor which you can configure. So you can configure replication factor manually also. So these are the two possibilities which exist. Replication factor can be configured manually. By default, the replication factor is 3. So when got it?
Yeah, quick thing here. So this looks like kind of a high availability stuff, right? Load balancing thing. Could I assume that's right?
There are two reasons for replication. One is obviously high availability, in the sense that one node fails, then still the system is available. Okay, so that there is replica on the other place. The second reason is throughput. Okay, because if one node is busy and the block is sitting there, then it has to wait for processing. Correct? If you replicate the block in 3 places, you have possibility of running the same program in 3 different places, so that you can get a better throughput. So replication is not only for availability, it is also for throughput.
So when we fetch the data, so which route it's supposed to take it? I mean, which?
That the system will, no, that is the system will take care. And when we look at job tracker, that is the next framework, the framework will take care of it. You don't have to worry. There is something called as speculative execution and all. It will check whether somebody is busy, it's not responding. It will spawn out another thread, go to another machine and so on. So that is where Hadoop is very, very flexible, and it has a lot of intelligence built in into it, so that it will use all this kind of tricks to make the things more faster.
Okay.
Okay, so for now, let's assume that there is a replication factor of 3 and each block will be stored 3 times, which essentially means there is a lot of space wastage. So if I am storing 1 TB of file into a Hadoop cluster, it will actually store 3 TB. But disk is cheap. So that is the reason we don't too much worry about the disk. Because these failures are common, availability is more primary important, and we can do. So now you got the level 4 view of it. Replication is possible and it is required. If you don't want replication, you can set the replication factor to 1 or 2 or whatever you want. But the problem is reliability will come down, throughput will go down depending upon how the system behaves. Any questions? So this is how the file system works. So you install a process called NameNode. NameNode has some configurations and based on the configurations, the client actually connects to it. Now, NameNodes, the data node reports the status back to NameNode. Now this is the level 4 view. So all periodically every NameNode will report back to the NameNode and stays the status of the file system. So how many file size is available, how many is free, how much is utilized, all this is reported back to NameNode. So NameNode has the consolidated view of the cluster. So that is how this 3 TB view is coming in. So when the new system is installed, you install this NameNode, you install the data node, immediately data node will say I have this much free space, this much free space, this much free space. So each will report 1 TB to him. So NameNode now knows I have 3 TB available. So that's how the virtualization happens, or the virtual aggregation of the disk happens when the NameNode is getting registered by the data node. So NameNode never pings data node. Data node always pings the NameNode. So that is the scalable model. If you have 10 data node coming in, each guy will ping NameNode and update the status. If they don't update the status in a specified time, it is considered dead. Okay. So if this data node doesn't report the status back to NameNode, it is considered dead. So then when the next request comes in, it will find out where the remaining blocks are there and it will serve from there. Okay, all this is transparent to the user. So that's the level 4 view of it. And the last view of it is you have access control which you can do on the NameNode. So each file has a privileges which you can set, which user will have. So that is a privileges are a meta level, data level property. It has nothing to do with data nodes or anything. Data node doesn't understand even the privileges. It is all handled at the NameNode. Okay. So the privileges of the file and so on exist. So this is where we will stop for today and we will continue from there on. Okay. Any questions? So we will continue day after tomorrow, not tomorrow. We will continue on Friday, the further one, and that will be a hands-on session where we will install the machines onto it and we'll do some practice of putting the file into Hadoop, taking the file and so on. So the HDFS part we will cover. Okay. Any questions?
Yeah, Sudesh, are you recording all this session like with the voice?
Yeah, it is all recorded. You will get it. You get a video, YouTube link for this. Okay.